Hello there. This video is on section 4.8, where I'm going to be showing you how to use the Newton-Raphson method to find a solution to pretty much any equation. This is a calculus-based approach at finding officially an approximation to a solution to an equation, although the approximation can be to any degree of accuracy. You want 3 decimal places of accuracy, the Newton-Raphson method can do it. If you want 100 decimal points of accuracy, the Newton-Raphson method can do it. So for all practical purposes, it will find an exact solution to any equation, so long as the equation is continuous and differentiable, so we can actually do derivatives and things like that. So let me show you how it works. It's an iterative process, which means we're going to be starting with a number, putting it into a formula, and the number we get out, we're going to put back into the same formula, turn around, get a new number, and we're going to repeat that process until we get the accuracy that we're looking for. All right, so I have here on the lecture notes sort of a paraphrasing of the Newton-Raphson method, which I think is more student-friendly, which is this right here. As long as you have some sort of differentiable and continuous function, and you have some value, I'm going to call it x1, that is reasonably close to a solution, right? We have a solution of the function equal to 0. If it's not equal to 0, you can just subtract and make it equal to 0. So any equation we can solve with this, but you have to start with something which is reasonably close to a solution. And then we're going to use this specific formula right here. This is a formula that's just the same formula as a local linearization. All these are applications of local linearization. So we're going to use that formula, plug in our x1, our reasonably close estimate, and we go through the formula and we get an x2, which is going to be essentially a closer estimate for our solution. And once we get that x2, we're going to plug it in and get x3, same formula. We're just going to plug in x2 now and get an even closer estimate, and we can repeat this process over and over again. So officially what's happening is we have an iterative process, which means the next guess, the n+1 guess, is based on the previous guess. And it's the same formula. And that has a limit, which means if we do it an infinite number of times, we actually get an exact solution. All right, well, that's sort of the idea behind it, the mathy thing. Let's just see an example or two so you can get a better grip of how this is actually working. All right, so I have my first example right here where we're going to try to find an x-intercept of this function. If you remember, the definition of an x-intercept is a value of x when y is equal to 0. So to find an x-intercept, we need to find when this is equal to 0. So this is x-intercept. All right, so the first thing we need is a reasonably close estimate for this function. And there's different ways of doing it. I recommend just using a table or a graph to get a reasonably close estimate. Now, this is a little bit of a tedious process, so I'm going to try to make it as, obvious as possible, as, but it's just all numbers, so I apologize if it looks a little confusing. This is the function y equals x cubed minus x minus 2. You can see the graph. There's an x-intercept right here. Desmos says the x-intercept is about, well, there it is, 1.521. That's accurate to 3 decimal places. What we should really be doing is not using technology. This is sort of a idea of using calculus instead of using technology. So you could say, well, it's around 1.5. But I also want to show you that just using a simple table, here's the table of values here. -2 is -8, which is down here a little bit, down here. And then these are all the different values of x that I have prepared for you, and the different values of y. And I want you to just focus on the y values. So I focus on the y over here, -8, -2, -2, -2, +1. So between these two values, between x equals 1 and x equals 2, the y value went from -2 to +1. And the number is not important. The fact is it went from a negative to a positive. If it's a continuous function, the only way it can go from a -2 to a +1 is if it went through 0. So we know that there's got to be some 0, some solution between 1 and 2. So that would be another reason for us to say, okay, let's try 1.5 as an estimate. So here's my 1.5 that I prepared for the next step. So the first step is find some reasonably close solution. In this case, I'm going to be choosing x1 is equal to 1.5. I know it's between x equals 1 and x equals 2, so I'll just do that. And now we use this formula. We say, okay, well, we have an x2 value. Let me do it in red. x2 is equal to x1 minus the value of the function at x1 divided by the derivative at x1. So we just plug in the numbers. So if we plug in the numbers, we get x2, that's our new closer estimate, is equal to our x1 guess minus the value of the function divided by the value of the derivative, evaluated at, of course, our 1.5 guess. So I need to do some math. I need to do 1.5 and then minus this fraction. And I prepared this ahead of time, so you don't have to go through all the steps. But this is the tedious part where you plug stuff in. So here's the value of the function at 1.5, right there, negative 0.125. So I need the value of the function at our guess. I need the value of the derivative at our guess. And let me just write down the derivative just here, just in case you are wanting to see what I'm doing. So the value of the function, the definition of the function is this, and the derivative is just straightforward. It's a power rule, 3x squared minus 1. So that's the derivative function. And I'm going to already put the derivative function here on the second thing. Here's the derivative function, 3x squared minus 1. And here's where I stick in negative, or where's where I stick in 1.5. 1.5 has a derivative value of 5.75. So we have the value of the function, we have the value of the derivative, and we have our formula. Our formula says take the 1.5 number and subtract the fraction of the function at 1.5 divided by the derivative of 1.5. I'm flipping back and forth, so hopefully this is not too confusing. So here's where I did the value of the function. This is the value of the guess. Sorry, 1.5 is the guess. Here's the value of the function divided by the value of the derivative. 1.5 is our x value. If I plug it into the function, I get negative 1.25. That's the top part. And the derivative is 5.75. That's the bottom part. I do the math and I get a better guess. My better guess is 1.521739. I think Desmos gives whatever 9 decimal places of accuracy, something like that. So there's my next better guess. So now what do I do with this? Well, I'm going to put it back into the function. This is my x2. So x2 was 1.52. Uh-oh, I forgot already. 1.521739. 1739. I'm running out of room. Anyway, so it's a bunch of decimal places. So now I do my x3. And that's going to be the exact same formula, but now with our new better guess plugged in. So we plug in the x2 and the function evaluated x2 and the derivative evaluated x2. And that will give me my next guess. And so what do we get here? Well, we get our x3 is our new value, 1.5. Let's suppose I want like 4 decimal places of accuracy, right? Suppose I only got 4 decimal places of accuracy. So let's get 4 decimal places of accuracy. So to get 4 decimal places of accuracy, I actually have to go to 5 because there's rounding errors. So I'll do 5 decimal places. So 1, 2, 3, 4, 5. There's my 5 decimal places. And then I would subtract the value of the function, evaluate at this thing, and then divided by the value of the derivative, evaluate this thing. I use 5 places so that at the end when I round, I still get 4 decimal places of accuracy. So now I have to take this x number, 1.52174. I have to find the value of the function, the value of the derivative, divide those two. It's the same formula. So let's see if I did that ahead of time. So here's the value right here, 5 decimal places, 1.52174. So here's the function value, just to remind you, this is the function value up here, 0.0021. And here's my derivative at 1.52, and I get 5.94 or 7. So I just put that into my formula. Here's my 1.52174 number. Here's the function, here's the derivative, and I get 1.5213, stuff like that. So 52138. And I can keep doing this forever, really. I just keep going on and on and on until I get accuracy of what I'm looking for. So how do I know when to stop? Well, in the homework, sometimes it'll say, do the process 3 times or 4 times, and then you'll know how to stop. But if you don't, if you just have some vague direction, like get 4 decimal places of accuracy, then you will have to go until literally 4 decimal places are accurate. So let's see, this guess was 1.521, so 14. So if I round this, oh no, 52138. If I already rounded it. So 52138. This one was 5217. So the fives matches up, the twos matches up, but the 7 is different than the 3. So far we only have 3 decimal places that match up. We do not have 4 decimal places, right? The first 3 decimal places are exactly the same, but our new guess changes in the 4th decimal place. So we have to keep going. So I take my new guess, my 1.52138 number, and I do it again. So here's my 1.52318 number, and here's the value of the derivative, and up higher here is the value of the function. And once again, I do my guess, my x number, the value of the function divided by the value of the derivative, and I get this thing right here. So hopefully I'm not doing this too quickly. It's just crunching in numbers. The value of your guess, value of the function at the guess, divided by the value of the derivative of the guess, it gives you a better guess. So this guess is 1.52179 round state. So 1.52138. 52138. 52138. So this next guess, I'm never going to write down the steps. 1.52138. Okay, now check this out. So here, the first 4 decimal places are the same as the previous guess. So in our X3 guess, we got an answer of 1.532. In our X4, we got the exact same to the first, actually 5 decimal places, but we need the first 4 decimal places. We're going to round it. So since there's an 8 here, we're going to say that to 4 decimal places, we know that this is the, whoops, what did I do wrong here? 5214. There we go. So this is going to be our solution accurate to 4 decimal places. 1.5214 is our x-intercept for this function, and we found it using this Newton-Raphson method. So that's essentially what this section is about. They're going to give you equations to solve, and you're supposed to use this iterative method, the Newton-Raphson method, to find a solution. So I'll do a couple more examples of this, but there's really nothing new I'm going to be doing. I guess there's a slightly new thing that I'll show you on the next example or two, but not much. This process is the process. We're going to do it each time. Okay. Yeah. So yeah. So that's my answer right there. So let me go turn this off and do the next equation. The next equation is this one right here. So I'll show you what that looks like on the lecture notes. Wait, page 2. All right, so on page 2, let me zoom in a little bit here and recenter this thing. Okay, maybe zoom in some more. All right, so we're supposed to estimate a solution to this equation using this particular method, this calculus method. If you haven't, thought about pausing the video and giving it a try, just remind you, it's a great way of learning. So give this a go. And I'm going to do the process again for folks to make sure they see it again. And then if you've come back now, I will now show you the solution. If you just want to see another solution, that's fine too. So I'm going to go ahead and do this. So remember, I need to have a guess. I need to have an X1. And that's going to come up with me using a table or graph. And then I'm going to, based on my X1, get an X2, which means I'm just going to do this little formula thing here. and it requires the derivative. That's why the function has to be differentiable, because you have to go plug in the derivative here. And we repeat this process so that we get any new guess is going to be the previous guess minus the value of the function at that previous guess divided by the value of the derivative at the previous guess. So that's your Newton-Raphson formula. Okay, so let's try to find an x1. And once again, we're going to make a table. You can make a table by hand if you had no technology, but I'm too lazy. I'm going to make a table using technology. So here's my function. You can see it actually has two x-intercepts here and here. So we're only going to find one, but you could do this twice and do the process all the way to find one solution and then repeat with a different starting x1 value to find the other solution. So here's a table of values I have here. Again, if you focus on the y values, it goes from -17 to -1 to 1. So when x is -2, y is negative. When x is -1, y is negative. When x is 0, y is positive. So between x equals -1 and x equals 0, it's switched from negative to positive. So I would choose something like maybe a half, right? X equals x equals negative a half would be something between -1 and 0. So around -0.5, it would be a good guess for this solution on the left. And if I do this, I think Desmos says that the -0.724 might be even better guess. But again, I'm trying not to rely on technology. I'm trying to rely just on calculus and basic, calculations to make this method work. You can continue on. You can see that between x equals 1 and x equals 2, y goes from a +1 to a -13. So we know there's another solution between +1 and +2. So that would be like 1.5. That would be the solution over here. Around 1.5 would be the solution over here. If you want it 3 decimal places, Desmos probably uses Newton-Raphson to get this solution. There are ways of doing it besides Newton-Raphson, but it's a nice, easy method for computers to use. So they probably did it to 3 decimal places of accuracy and got 1.221. But my guess would be about 1.5 for the starting value of the solution on the right-hand side here. Okay, so I need my derivative. So I got my original function. So my original function, I'm just going to write f of x equals this, even though it doesn't have fx in there. I'm going to write this so that I can sort of remind myself I need to take the derivative. So the derivative here is -4x cubed plus 1. So that's my derivative formula. And then what I'm going to do is I'm going to be finding some x value and plugging in the value of the function at that x and the value of the derivative. If you want, the way your textbook does this is they actually translate this a little bit into like the formulas. So the way they write this is they write x n plus 1 is equal to xn minus, and then they take the function value and plug in xn. So they would say xn to the 4th plus xn plus 1. They're basically just saying I'm plugging in that value. And then on the bottom, you would do -4 xn cubed plus 1. For a lot of people, this is confusing with all the n's and stuff like that. But they're just saying, plug on the xn to the function, plug in that xn to the derivative, and you get this formula here. All right, so what I've done here is I've done just that. I had to write it as y's and x's because Desmos gets a little confused with all the x2s and xn's and stuff like that. So this is my next guess. Y is really my xn plus 1. And here's my original guess, x. And here's the value of the function at x. And here's the value of the derivative at x. So now I just have to put in some x values to be able to find a solution. And our first solution on the left was around x equals -0.5. So here you can see I've actually made a little table of values here. Let me scroll this down a little bit so that goes up. Okay, so you can see that I've tried x equals -1.5, and it gives me an output, which, remember, according to our formula, is just the next guess. It's just I plug it into the formula and I get the next better guess. I know it says y here, but that's just because Desmos is a little bit wonky with variables. So that's my next best guess. So here's my first guess, negative 1.5. I plugged into my formula. I get, I get my next best guess for X. I plug that in. I get my next best guess for X. I plugged it in, and I keep doing this over and over and over again. I have like each guess I get, I plug into the next, input value, and I get my better guess, plug it in, better guess, plug it in, better. So this is a much more efficient method than the way I used before, where I had to like have two separate tables, and then I had to type stuff in, and then I type a different stuff in. So this is sort of a lot more efficient in terms of doing all the steps. So here's the formula, and each time I plug it in, I get a better and better approximation. You can also see the degrees of accuracy here, are the decimal places of accuracy: 7916667, 729. The sevens have matched up, but the next decimal place has not matched up. And when I round it, it's even different. So not a lot of decimal places of accuracy in the first couple, but then it starts settling down. We have 729, 724, 724, 724. So 7245, 7244 rounded to 5. So you can see that it gets closer and closer and closer to a limit, right? It gets closer and closer and closer to the exact solution to the equation. And depending on how many decimal places of accuracy, I went to farther here. I went one more. You can see 7244919. So as far as the accuracy of Desmos goes, it all matches up. So that's, I think, 7 places of accuracy for this particular problem. So you could have also done the solution on the right-hand side, which means I would start with 1.5 as, going to work for me. Here we go. I would start as positive 1.5 as my starting seed value, and I get 1.295, which is a better guess. I put 1.295, and I get a better guess. And I just keep doing this, getting better and better guesses. Again, tedious, but not maybe so much so as previously. And I keep doing this over and over and over again until I get the desired level of accuracy. So this is sort of more in line with the way the book shows it, where you just use one big formula and you plug stuff in and you keep getting better and better estimates. So nonetheless, with the left-hand solution, negative 0.724499196 would be my very accurate solution to seven decimal places of accuracy. All right, so I'm not going to rewrite it here, just done on Desmos. And if this was a test, I would just attach a screenshot to show my work, because you're supposed to show work. And I'll just pause the video and I'll write my solution just so it's on the lecture notes as well. You gotta pause it. Okay, so I just transferred the number over from Desmos. And that's one solution, right? This is just one solution. And then if it asks for both solutions, you'd have to do the other solution, which you started to do, but we didn't do all the way because, it's just a lot of tedious doing the same thing over and over again. But it starts off with 1.22 or 1.23 something. So it's, 1.2 something, something, something. We'd have to do more iterations to get a better approximation. All right, and the very last thing I'll show you with the Newton-Raphson method that may be slightly different is an instruction like this, which doesn't really have the appearance of like an equation you're solving. It says approximate the cube root of 50 using the Newton-Raphson method, which is a method using calculus. You're taking derivatives, plugging into a formula. There's no function here. There's no derivative here. So some students get a little confused with an instruction like this. So I wanted to show you the approach that we use, the calculus approach, for just a question like this, which doesn't appear to have like an equation. So we do need an equation. And since we're trying to find this value, we're trying to find the cube root of 50, I am going to write x equal to cube root of 50. So I guess in math, we would say let x. So we've invented a letter x. So we have an equation and we're looking for x, right? We want to find x, right? So we want to approximate x. right? So that's what we're looking for, is to approximate x. So let's make this a little bit easier to work with. Let's cube both sides. So I'm going to take this thing on the left, thing on the right. We'll cube it. I get x cubed. The cube will undo the cube root, gives me 50. And then I subtract 50 on both sides. So I minus 50 on the, on both sides. And I get x to the third minus 50 is equal to 0. So that looks now like our previous problem, where we had 0 is equal to some formula, and here we have 0 is equal to some formula. So essentially we're saying is, let our function be x to the third minus 50, and we want to find the solution to 0 is equal to x to the cube minus 50. I want to find x, right? This is supposed to be a minus. And then, of course, we would just find the derivative. We would take the derivative of this thing, and that would be 3x squared. And then we plug it into our formula. So we have xn. Well, I'll write out the formula using the n plus 1s and stuff. Xn plus 1 is equal to xn minus the value of the function at xn divided by the value of the derivative of xn. Or using our formulas, xn would be our guess. Fxn plus 1 would be when I plug in x plus 1 into this thing. Xn into this thing. And then divided by the derivative. The derivative is right here. So I plug the derivative in, or plug the function, the value of the function into that derivative. And then what I would do on Desmos, just because all the xn's and x plus 1, n plus 1s are just difficult to deal with using most technology. So I would say let's let this thing be called y, and it'll do x minus x cubed minus 50 over 3x squared. That would be the formula that I would plug into Desmos, and then I would find a solution, and I would iterate the process over and over and over again. Now, I don't even need a table to make a guess for this guy. X cubed minus 50, or x cubed equal to 50. I'm looking for a number raised to the third power is 50. 3 times 3 times 3 is 27. 4 times 4 times 4 is 64. So I know it's between 3 and 4, just because I know like multiplication tables, right? So I might choose my first guess to be something like 3.5, because 3 cubed is 27 and 4 cubed is 64. And so I know to get 50 as an answer, it's got to be between 3 and 4. So maybe I'll choose 3.5. Right. And then I would go to my my Desmos. I would type in my equation, y equals x minus the value of the function, which is x cubed minus 50, divided by the value of the derivative, which is 3x squared. So that's, let me get rid of these other random graphy things so it doesn't look so confusing. So that's the formula. I'm going to change this into a table by going to this little wheel and saying, make a table out of it. There's my table. It starts with some values. I'm not going to use their values because I don't need them. I know my first guess is between 3 and 4, so maybe 3.5. And that gives me this 3.69 number. I do believe there's a way of copying and pasting, which I forgot. So I'm just going to type it in. 3.6938776. And there's my better guess. And then I'm going to keep doing this until I get whatever degree of accuracy they were looking for. 3.6840577. Hopefully I've explained this clearly enough to see what's going on. You just keep typing in better and better guesses until you get the degree of accuracy you're looking for. You can already see I'm pretty close. 3.68405 versus 3.68403. So already just with a couple of iterations, I've gotten a pretty good guess, assuming 4 or 5 decimal places is a good guess. So that is a Newton-Raphson method. And there aren't really any other tricks they're going to throw at you. I just want to make sure you know how to do that, like solving a random approximation by turning it into an equation and then doing the same formula again. Once again, hopefully you found that useful, and please reach out if you have any questions, want to go over anything, or see additional examples. And I hope you have a very enjoyable day.